What's up, everybody? Let's look at this bungee jumping FRQ. Essentially, we are jumping off a platform and we're attached to a bungee cord, and we're going to see what happens as we almost but not quite reach the ground. So the first part of the question is asking basically to analyze the energy transformations, like what's going on at various steps. Actually, in the key, they're only looking for the beginning and the ending, but the way I read this question is they're looking at it for the entire journey. So let's go and do it that way. So at the beginning, at the very top, hopefully we'll just call this initial state. At the initial state, we have both kinetic energy and potential energy because, well, we're above the ground, we're moving, and the bungee has not been stretched at all. Okay, as we fall, essentially the kinetic is increasing and the potential is decreasing, right? We're falling towards the ground, getting faster. We have not stretched the bungee yet. Somewhere, let's say maybe like right here, we're going to start, the bungee's going to start stretching as it starts to slow down. So at that point, so that's case, let's just call that the beginning. Number 2, as we fall. Number 3, we'll say when the bungee starts stretching. When that happens, we're going to slow down a little bit, right? And so that means our kinetic energy is going to be decreasing. Now we're still falling, so our potential energy is also decreasing, which means something must be increasing. And yes, of course, that's going to be the elastic potential energy within the bungee cord, and that's going to be increasing. And then at the end, when we stop, okay, and this is the actual final state, we at that point we're not moving, right? So we have zero kinetic. They do define this H point as our reference point, so we're going to say that UG is also 0 since we have no more height. And then finally we'd have our maximum, and let's just put all the energy is now going to be contained within the spring or within the bungee. So in the key, they're just asking about number 1 and number 4. But again, I think it's better to kind of go through this whole process of what's happening through the whole journey. All right, question 2, we're looking to essentially derive the equation for the spring constant. So we're going to try to figure out what the spring constant is in terms of the variables that are given. So hopefully you notice way back here, actually we just did it in the last problem, we know that at the top we have all UG and KE combined, and then at the bottom it's going to be only spring potential. Okay, so we're just going to go ahead and substitute in. So we're going to go mg height. Now remember, this, we called this our 0 point, so that means the actual height here is going to be d minus h. So d minus h plus 1/2 mv squared equals spring potential 1/2 kx squared. Okay, and then we're just going to go ahead and solve for k. So k equals, multiply by 2, divide by x squared, and we're going to end up with 2mg d minus h plus, cancel that half, mv squared, and then we're going to divide that by x squared. Now again, you always want to go back to your original, what they're allowing you to use, and just check your variables. So d is good, h is good, m is good, g is good, m is good, v is good. X is not good, so that's not one of our choices. So we do have to solve for x. So recall, if we go back here and look at this, from here to here, let's say this is the unstretched length before it starts to stretch. So let's say at this point the bungee just starts to stretch, and it's going to continue stretching till it stops. So this is what we're defining as our x, this distance right here. this is D, right? All the way down here, this is D. And then we have our little h right here. So that's h. So hopefully you can notice that D is equal to L plus X plus H, which means X should be equal to D minus L minus H. Okay, so that's going to be X. You're just going to go ahead and throw that bad boy into here, and you are going to square that out, and you should be good to go. So the last part of the question is saying, what if you do not ignore air resistance? How would that affect things? And specifically, they're asking, how would that affect how much it stretches, the stretch length? So hopefully you notice it, if as it's falling, if this is happening, there's going to be work done by air resistance, right? It's essentially going to be taking away energy. So it's going to remove energy from the system. So if we're removing energy, or we often talk about energy being lost, then we need to put this as a part of our equation. So we could say, well, there's going to be some energy lost here. Well, if there's energy lost, that means that the spring potential that you end up with is going to be less than what you started with, all the energy you started with. So that means that the net result is, actually this is letter B, that means the net result is the string L should decrease. Actually not L, this is X, right? X should decrease because essentially some energy is being lost. Energy lost to air resistance, work from air. So there's less energy to stretch. Okay, and there's other ways you could explain this, but that's, the major concept, the major thing you should be looking at. Let me know if you have any questions.